Hi everyone, this is the last video for section 5.3 and the last video for chapter 5, where we're just going to do a few more examples of GCF and LCM. Okay, so this first example says the factors of a number include 9, 12, and 30. And we know that these are factors of the number, and we want to know what is the smallest number this could be. And then we'll solve the factors. So what this question is really saying, this is just a different way to ask for the LCM. Because if we know what the factors of a number are, and we know that we want the smallest number that's a multiple of these things. Right, so remember that there was this kind of equivalent way of saying that if A is a factor of B, then B is a multiple of A. So this is all this is saying, is kind of translating between they give you the factors and they want to ask for a multiple. So this is just saying to find the LCM. So again, we're going to do this using the prime factorization. So 9 is 3 squared. 12 is 2 squared times 3. And 30 is 2 times 3 times 5. I wrote these kind of quickly just because we kind of talked through these in previous videos. Okay, so again, we want to find the LCM. So remember that we can draw a Venn diagram if we want to. I'm going to do the Venn diagram method here because I have not done it for 3 numbers. So if we have 9 and 12, well, I'll make the 12 here and the 30 here. So they all have a 3 in common. And 9 has one other 3 that no other number has. Okay, so 12 has 3 and 2 2's. So one of the 2's it has in common with 30, and one of the 2's it only has itself. And then 30 has that 3, that 2, and a 5. So I know I did that kind of quickly, but you can see that all 3 of them have a 3. And then the only one that has 2 3's is 9. Okay, you can see that 30 is the only one with a 5, and it has a 2, and 12 also has a 2, but 12 has one additional 2. So this is how you kind of draw this Venn diagram for 3 numbers. So from here, we can get that the LCM of 9, 12, and 30 is 2 squared times 3 squared times 5, which is 4 times 5 times 9, which should be 180, 20 times 9. Okay, so that's the LCM is 180. And now we want to list the factors. So we can do this in a number of ways to think through this. We can start off just by using the prime factorization. So we know that 1 is always a factor, and 2 and 3 are in the prime factorization. And then 4 is 2 squared, so 4 is there as well, and 5 is there, just based on the prime factorization. 6 is a 2 and a 3, and 6 is there. 7 is prime, and it's not in the prime factorization. 8 is 3 2's, and we don't have that many, but 9 is 3 squared, and it is there. 10 is 2 and 5, and it's there. 11 is prime, that's not in the prime factorization. 12 is there, right? This is from the problem that one of the factors is 12. 13 is prime and it's not there. 14 needs a 7, that's not there. 15 is a 3 and a 5. And there comes to be a point where you can start noticing patterns. Well, let's get to the next one, then I'll start talking about the patterns. 16 needs 4 4's. 16 needs 4 2's, which we don't have. 17 is prime, it is not there. 18 is 9 and 2, which is there. So this is 18. And now. So now comes the point where you can start finding a pattern where lots of times you do factors in this way where you say, okay, we have 10 times 18. You can also say that you have 10 times 18 is 180, but there comes a point where everything leading up to a certain point then gets multiplied by everything from a certain point. So that point right here is at 12. So 12 times 15 is going to give us 180. So now everything on the other side of 15, everything on the other side of 12 is going to be what's multiplied by the number before it. So let me just kind of rewrite this a bit. So 12 times 15 is 180, and then 10 times 18 is 180. And then we can just kind of divide 180 by these numbers. So for example, 180 divided by 12 is 15, 180 divided by 10 is 18, 180 divided by 9 is 20, 180 divided by 6 is 30, 180 divided by 5 is 36, 180 divided by 4 is 45, divided by 3 is 60, divided by 2 is 90, and then we just get 180 as the last thing in the list. So yeah, there comes a point whenever you're listing out the factors that there's some transition point where all of the numbers you cannot multiply together to get 180, but then once you get to this point of 12 where the thing right on the other side of the division line, right off the other side of this dividing vertical line, is what you multiply that number by to get 180. So I hope this made sense. I would really hope that you've seen this pattern before. Okay, so those are all factors. So now we're going to do another example. So if 21 divides m, what other numbers must divide m? So this is kind of combining things that we've talked about before with this concept of divides in the first section. The first section of chapter 5. So if 21 divides m, what other numbers must divide m? And so specifically, this is talking about that product. So this is talking about the product property of divides. So let me just write that down. So the product property of divides. Remember, it says if some number n divides a, then n divides any multiple of a. So if 21 divides a number, then this actually isn't the product property. My apologies. Thought it was. It's for something really simple, but you can just kind of think of it logically that if 21 divides, so say that 21 divides a number n. Okay, I see. This actually is using a property we didn't talk about in section 1, that this divides is transitive. Remember that the transitivity property from when we talked about the properties of equality? This essentially is saying that if 21 divides m, then any number that divides 21 must also divide m. So any number that divides 21 also divides m. Because what does it mean if 21 divides m? That means by the definition of divides that m can be written as 21 times some number n. Well, the factors of 21 are 1, 3, 7, and 21. So this can also be written as 3 times 7n, 7 times 3n, right? So we can rewrite this 21 as a product of its factors, and then we can see how any factor of 21 will also divide n. So we just need to list out the factors of 21, which are 1, 3, 7, and 21. So 1 always divides everything. We're given that 21 divides this number. So that means that 3 and 7 must also divide this number, just because we have this substitution and the association of multiplication that we can use. Okay. So the last example is one where we actually are going to practice using the Euclidean algorithm. So I know I said before that you just needed to know what it said, but I think it can be really unclear what it means if you don't do an example of it. So we're going to do an example using the Euclidean algorithm just so you can see why it's useful, because it is really useful. It just is hard to understand unless you see an example of it. Okay, so we want to find the GCF. We want to find the greatest common factor of 850 and 918. So this is an incredibly large, these are really large numbers that would have a lot of factors. So rather than trying and listing out all the factors of these things, we can use the Euclidean algorithm. So the Euclidean algorithm says that the GCF of these two numbers is the same thing as the GCF of the smaller one and the remainder when you divide them. So let's divide them. So if we divide 918 divided by 850, well, this can go in once, and we will have a remainder of 68. So this remainder here is 68. So these two things are equal. And this is what the Euclidean algorithm tells us, that the GCF of two numbers is the same as the GCF when you divide one by the other. Okay? So again, 68 and 850 are numbers too big for me to want to deal with. So we divide again. So now we do 850 divided by 68. 68 goes into 85 once, with a remainder of 17. 17, we bring down the 0. 68 goes into 170 twice, with a remainder of 34. So this becomes the GCF of 68 and 34. So again, we can repeat this division process. So now we do 68 divided by 34. And let's say 34 goes in there 2 times, which has a remainder of 0. So this is 0. Okay, so, right, we have that little note that said, it was up here, a note that said, the Euclidean algorithm is most effectively used when repeated until the remainder of 0, then that divisor, the divisor that gives the 0 remainder is the greatest common factor. Okay, so that tells us here that this is the greatest common factor that gives a divisor of 0. It's 34. So this is kind of how you use the Euclidean algorithm. You can just simplify the greatest common factor over and over again. And so you could have potentially noticed it at the GCF of 68 and 34 and noticed that 34 times 2 is 68. But if you don't, you can just keep dividing until you get that 0, until you get that remainder of 0. And at that point, right, the greatest common factor of 34 and 0 is just going to be 34. So this is a simple, not a simpler way, but just a different way to go through it and simplify the GCF until you get something that's easy to see. So that is an example of how to do the Euclidean algorithm. The examples that they give, they only give one real example in the book that has numbers that were a little bit smaller. So I just wanted to give you an example that was a little bit bigger. Okay, so that's all for chapter 5. This is the end of the chapter 5 videos, and we'll keep going with chapter 6 later.